Hello, everybody. I'm Zach. I'm the CEO of Aztec. We are a end-to-end encrypted blockchain layer 2 for Ethereum, where we have privacy by default. So I want to talk a little bit about how to keep a secret. So Aztec is a privacy-preserving layer 2. Very much following the footsteps of networks like Zcash. We got started in 2017, and it's been a long road to get to where we are today, which is fully composable, privacy-preserving smart contracts. So if you have a private blockchain, you have to have some very interesting state models, because the regular way that blockchains work with account-based state doesn't really function properly if you want to preserve privacy, even if you encrypt the state. So I'm going to talk a little bit about that. Basically, why is keeping things private hard? How does it work in practice? And how can we create abstraction layers so that regular engineers, developers can build smart contracts, can construct applications without having to know any of these really, really messy details that require cryptographic knowledge. So why is encrypted state hard? So this is the Aztec network's architecture, I believe. So this is a few years old. It's grown since I last screenshot it. It's tricky. So let's try to simplify it. So the basic way that there are two basic ways of state models in blockchains. You have account-based state, and you have UTXO-based state, so unspent transaction objects. Bitcoin is UTXO, Ethereum is account-based. And account-based is by far and away the nicer way of doing things, because it creates much more natural ways of constructing contracts. Because you have some Merkle tree. The leaf in the Merkle tree is, each leaf in the Merkle tree is basically some storage slot of a smart contract. And the problem with that is, if you imagine you encrypt the Ethereum blockchain, and you have some way of modifying those encrypted values, you still leak a lot of information. Because if I were to send some Ethereum to everybody in this room, well, you may not, observers won't see the values being transmitted, because just a bunch of encrypted values will change in the database. But they will see that there'll be one specific balance in that ledger, my balance, that will change 100 different times. And so effectively, what happens there is the transaction graph gets leaked. And that basically means that you don't have anonymity, because all that happens is that your Ethereum address, instead of it being your address, it just becomes your encrypted address. It becomes a position in the state tree that where the values change when you perform transactions, which isn't private. So that's a pain in the ass. And then you have the unspent transaction model way of doing state, which is much less intuitive. The idea here is that you have leaves in a tree, but instead of them representing accounts, they're discrete quantum values. So if I have one Bitcoin, I may have a single leaf in a Merkle tree that says there is one Bitcoin and it's owned by Zach. Or I may have 5 different leaves in a Merkle tree, which each say this is 0.2 Bitcoin and it's owned by Zach. Basically, a user's balance is now no longer a single value in a database. It's a composite value of lots of different leaves. And the way that you spend a note in Bitcoin is you nullify it. So basically, you tag it as being deleted. The Bitcoin model is much more amenable to private state, but it's a faff to work with because of the fact that your state is kind of composed across multiple different values in a database, which lends one of the issues around doing privacy. So how does encrypted state work in practice? So this is some basic stuff where, so you've got some generic state that's being generated by a smart contract. So you take the value that you want to store, you take a storage slot, so an identifier that's defines which state variable in a contract that value belongs to, and you hash it with the smart contract address. This ensures that you have some level of uniqueness. Multiple contracts can't create values in your state tree that overlap. What's missing here is if this is encrypted, there needs to be a secret, which is missing in this diagram. But yeah, you'd add a secret in there as well, and voila, you have something encrypted that nobody who that you need the secret key to understand and decrypt. And the way this works is actually I'm going to go back a couple of slides because slightly out of order. How do you get privacy with a UTXO-based tree? The trick is that your state tree, your Merkle tree that defines your the values in your blockchain, you can't delete values from that tree, and you can't modify values that have already been created. It's append only. You can only add stuff to that data set, which is a problem, right? Because how do you spend value? How do I send somebody some Bitcoin if I can't delete my own Bitcoin? The way that works is with this nullifier set, where you have a database of nullifiers, and if a note has a nullifier, then it's considered deleted. So in order to spend a note, to destroy it, I have to both prove that that note exists in the state tree and that its corresponding nullifier does not exist in the nullifier set. Well, why is this useful? It's because the encryption algorithm that's used to encrypt nullifiers is different to the one used to encrypt notes, which means that, let's say I do a basic encrypted transaction. So I send somebody. So I have a note that's worth 1 Bitcoin. I delete it. I create 2 notes that are worth half a Bitcoin. One of them's owned by me. One of them's owned by a recipient. Well, what does an observer see when that transaction gets mined? They see that 2 notes have been created in the state tree, and they see that 1 note has been nullified, but they don't know which note's been nullified. So they don't know who owns the new notes. They don't know who owned the note that got destroyed. And so you've completely broken the transaction graph. This is pioneered by, I believe, the Zerocoin paper and initially the Zcash protocol. This is how Zcash works. And what we're doing at Aztec is we're just extending this concept to cover, instead of it covering just values, cryptocurrency values, it's just, this concept covers generic state. So smart contracts, instead of them just recording values, they have this kind of storage slot and data tuple, which means that you can encode arbitrary information in these kinds of databases. So how does it work then in practice? There are generally 3 ways of using private UTXOs. You have something we call an immutable singleton, which is basically a smart contract can create some data that never gets changed, never can be destroyed. This is very useful because for these kinds of singletons, obviously you don't have nullifiers, which means it's much easier to check the value of one of these notes in a ZK SNUC. You then have this concept of a mutable singleton. So this could be things like an initialization flag. It could be something like a whitelist token. The idea is that there's only ever 1 note at a time, so it doesn't represent a balance. It's more like an NFT type of entity, which can be replaced. It can be updated. The way you update things in this model is you have to delete your original note, nullify it, and then create a new one in its place. The reason for this is to, again, break the transaction graph. So let's say I have an NFT, and I can change some properties on the NFT. Let's say it represents some kind of CryptoKitty, and I'm mutating it somehow. Well, what would happen is that an observer who looks at my transaction would just see that something got nullified and something got created. You wouldn't know which smart contract created the state. You wouldn't know who owns it. You leak no information whatsoever, but it does require this process of nullifying a state variable and then recreating it in your state tree if you want to change it, which is a pain. And then you have this concept of a set to represent a balance. The idea here is that your balance is represented by the sum of many notes. This is what Bitcoin and Zcash do. It's a bit of a pain because it means that your balance isn't really is defined by an unbounded set potentially of notes. This also makes it somewhat challenging to write smart contracts for, because in this kind of model, let's say you're writing a smart contract on the Aztec network. It's not possible for a smart contract to validate that a user has provided all of the notes that represent that balance. Let's say I have 5 notes that represent my Bitcoin balance, for example. And there's a smart contract that wants to know what is my Bitcoin balance. Well, when I'm constructing a zero-knowledge proof, I could just provide 4 notes. I don't have to provide 5. There's no way the contract can validate, oh, right, this person was supposed to provide 5 notes. The size of the set is unknown to a smart contract. And it has to be this way, because imagine somebody wants to send me a note. So there's a transaction that happens on the Aztec network. I get a shielded Bitcoin. So I used to have 5 notes, now I have 6. I might not. How do I know that I have 6 notes? I have to sync to the state tree. I have to decrypt it. But it's not possible to have like a value in that database that says Zach owns 6 notes, because for that to be the case, when somebody is giving me a Bitcoin note, they would need to modify that value, and that value is encrypted by me. They don't have that knowledge of that value. They don't know where it exists in the state tree, because the simple act of if a user knows, okay, well, if I'm going to give Zach a Bitcoin note, I need to increase his number of notes he owns, which means there's a specific note in the state tree I need to modify. That knowledge leaks information, because if a random person knows that, everyone knows that. And then everybody can see if that value gets modified, even if they can't decrypt it, they know, oh, Zach's received a Bitcoin note. So this concept of an unbounded set is an additional complexity when writing smart contracts that manipulates private state. And it's an interesting problem to try and resolve. So this is some more examples where, Alice has 2 notes, they're worth half an ETH. She deletes them both. She creates 2 new notes that are cumulatively worth half an ETH, but she sends 0.4 to Bob. Well, again, this is effectively a balance transfer, but no observer can see what happens by looking at Alice's transaction, because all that they see is there's a zero-knowledge proof, there's 2 new nullifiers that have been created, there's 2 new notes that have been created. What's actually happened under the hood? Nobody knows except Alice. And so, yeah, this is just highlighting the fact that these nullifiers are essential for breaking transaction links. So how do we create abstraction layers that begin to help with some of this complexity? First, I want to talk a little bit about the transaction model within a network like Aztec. With Aztec, every function in a smart contract is a circuit. So if I have, if I'm writing an ERC20 or ZRC20 or ARC20, I might have 10 different functions. They'll all be independent circuits. That's this is kind of very important for this concept of private composability, because if I'm writing a smart contract, I want my smart contract to be able to call other smart contracts that can call other smart contracts that can call other smart contracts. And the way this works in practice is that each function call is an independent Zk-SNARK proof. And that when a user is making a transaction, they construct all these proofs, and then they compose them all together recursively to construct basically a single proof of correctness of a chain of function calls that defines their transaction. And the overall verification key for a smart contract is basically a Merkle tree of the verification key hashes for all of the functions in that smart contract. And that becomes a unique identifier. So the abstraction layers we want to create are a bit like the following. So on the left-hand side, we have an Aztec private function. So it's coded in a language called Noir. Very Rust-like, easy to use, has nice semantics for modifying private state type, working with encrypted data. But when a user constructs a transaction that calls this smart contract, what we want to see is on the right-hand side. Like these are the only external things that this contract can do. It can call other private functions from other contracts or itself. It can call public functions. So these are functions that modify like in a public account-based state tree. These public functions are tricky because they're not, the proofs of them are not computer client-side. They can't be because of race conditions. When you're working with a UTXO model where users own their own state, then they can construct proofs of that modify their state. But if you have global account-based state and you want to modify that, you need to ensure that you have a problem where if multiple people in a block modify that same state variable, it's going to constantly change, and this creates a race condition where your proof will be invalid if you and somebody else have modified the same variable at the same time. So you need a sequencer basically to build a block, order the transactions, and then you have a prover network which will prove the correctness of those transactions, prove their public functions. And this basically means you have a time ordering issue where in a smart contract transaction, the private functions are executed first, and then the public functions are executed after the private functions, which means a private function can call a public function, but you can't have any return value from it because that public function is going to be executed after your private functions have been executed. So that's one of the other things that can happen, and you can emit encrypted events. You can add nodes to the UTXO tree, and you can nullify nodes from the UTXO tree. This is all that you can do from a smart contract. So effectively, like what the user's doing in a transaction is they're going to be, because we have account abstraction, you're going to be calling an account contract to validate who you are. You're then going to call one or more smart contracts, and then you're going to call some fee-paying contracts. But what the network's going to see from that is you have a zero-knowledge proof of correctness, and then you just have a list of nodes that are being created, nullifiers that are being created, public functions that are being called, and encrypted events that are being emitted. On top of the state root that was used in your transaction, because when you're basically spending nodes, you're proving that they exist in a state tree, and so you have to define which state tree you're using. This is another important reason why we have to have append-only UTXO trees. If I, as a user, want to call a smart contract that reads a private state variable, I'm going to have to basically construct a membership proof proving that this state variable exists within the Aztec data set. So I'm going to be basically hashing up to a Merkle root. And the Merkle root that I'm using can't be guaranteed to be the latest Merkle root of the chain, because that constantly changes. And so it's important that you can use old Merkle roots to prove the existence of state in the state tree. That is fine if your state tree is append-only, because once something exists in the state tree, it never gets removed. So what actually gets leaked out of this transaction? Like, what can a observer look at here and to determine whether this transaction is, like, what it's doing? There's obviously the public function calls are the big place where information gets leaked. So if you're creating hybrid smart contracts in Aztec where you have private state and public state, so for example, you're creating an automated market maker where the liquidity pools are public, the token values are all public, but the identities of the people trading are private, then you're going to be creating some kind of hybrid model where you have to be very careful about what public functions you're calling, because it does leak information. The fee value possibly could leak information, because if you're paying a lot more than other people, well, probably implies either you've got bad data about your fees, or this transaction carries a lot of value. But other than that, everything else is hidden. Like the notes, the nullifiers, the encrypted events, they don't reveal any useful information to the observers. And I think this is kind of quite foundational, because it means that within a network like Aztec, you can execute a bunch of smart contract calls, and effectively what you're telling the world is, I'm not going to tell you who I am. I'm not going to tell you what smart contracts I have called. I'm not going to tell you who I am transactioning with. I'm not going to tell you what I've actually done on this network, like what outcomes have happened. But I can prove to you that despite all this, I follow the rules of the blockchain network. So the smart contracts that I have called exist, and they've been executed correctly, and all of these state updates have happened according to the rules of these smart contracts. But you don't know who I am, and you don't know what I'm doing. And this is quite revolutionary. It means you can do things like you can instead of having an account which is defined by like a public-private key pair, you could have an account smart contract that verifies a signing in with Google flow or signing in with an Apple ID flow. And nobody knows that you've done that. Nobody knows that you've authenticated yourself using Google or Apple, except, well, maybe Google or Apple, because you've probably had to make an API request to them. But to the rest of the world, it's completely hidden. So yeah, I think, let me just check. Is there anything here useful? This is all, yeah, OK, we can skip this because I've only got 10 seconds left. Yeah, so I mean, I've only really touched the surface of how these encrypted state models work, but I'm very happy to take questions and yeah, chat more about this offline. Cheers.